I'm going to present you this game we are developing. This is done in collaboration with students, engineering students from Universidad Adolfo Ibáñez, where I work, and Universidad Santa Maria, which is also one of the universities involved in MPF. And the idea is to make a video game which is based on hydrodynamical simulations of protoplanetary disks, and to use it as an outreach tool. So yeah, we want to show protoplanetary disks, and nowadays we have a very good idea of how they look like, thanks to ALMA, for example, and other observatories. And here I'm showing you the first image that was published by ALMA. This is the disk of HL tau, and it shows that, and this is pretty much what we expected, I would say. So it shows a disk that is mostly axisymmetric with some gaps and rings, and this looks really pretty. So it was amazing to see it for the first time, like 7 years ago or something. And as I said, this is more or less what we expected. But also, we've discovered more and more that several protoplanetary disks are quite different. They show much more structure, they show asymmetries, they show spiral arms, they show large cavities. So there's a lot going on. And I'll show you two nice examples, but actually the more protoplanetary disks you explore, you find more and more of these structures, like spirals, large gaps or cavities, narrow rings, and so on and so forth. A possible explanation, not the only one, but a very interesting explanation, very promising explanation as well, is that this kind of structure is created by either binary companions, so another star that is in the same system, or planetary mass companions, so a planet that is already formed inside the disk. The example here on the left shows a binary companion, a star which is relatively massive. So it manages to, they both together manage to clear up a large cavity in the inner part, and also to drive all this spiral structure that you can see here in the image. A planet can do similar things, although typically the structures they create are smaller. So for example, here you see that the spiral is less prominent, and rather than a large cavity, there's a narrower gap. Now, in some cases, we are sure this is the correct explanation, or this is at least a large part of the explanation, because we actually observe that there's a binary companion or that there is a planet. But in many other cases, we are not sure. We haven't detected the companion yet. So this is just this is a plausible hypothesis, but it's not for sure. This kind of study is done with numerical simulations, with hydrodynamical simulations, and in which you put these ingredients. You put the planets, the stars, the disk, and so on, and let the laws of physics work, and you see what happens. This is another example of a hydrodynamical simulation that here I'm showing you an animation from one simulation. This is work led by Pedro Poblete, who was part of NPF until recently. And in this case, we had to include both ingredients. We had to include a binary in the center and a planet a little bit further out. So we needed both a binary and a planet to create the structure that we see in this system, HD 169142. Something I should mention is that current simulations can follow both the gas and the dust component of the disk. So these disks have those two ingredients, right? And they behave a little bit different. So on the left here, you can see the gas distribution. As you can see, the distribution is more extended. It is a bit more uniform, and it also tends to show spiral arms more easily. The dust, on the other hand, that we see here on the right, tends to create sharper features. So narrower rings, and and doesn't show spirals so easily. And so the same simulation gives you both components, and it's actually important to follow both components if you want to compare with observations, because in general, different observing bands show you different features of the same system. So these are images of the same system that Pedro was simulating, right? But these are actual images. And on the left, we have a near-infrared image, which more closely resembles the gas distribution. And in sub-millimeter, this is the ALMA observation. On the right, this is emission from the dust. So yeah, we need both the gas and the dust to explain the near-infrared and the ALMA observations. And you can see that they show quite a nice agreement. Okay, so after that short introduction to protoplanetary disks and how we model them, I'm going to focus on the video game, right? And what we wanted to do was basically take the numerical simulations, take all those data, and put it in a format that can be used, that can be enjoyed by the general public. So typically, the general public gets in the news, they see the pictures, the images taken by the telescopes. And that's perfect, that's really nice. But I think we also wanted to increase the depth of exposure to these ideas by letting them use the data of the numerical simulations. So we wanted to use actual simulation data. We asked our collaborators, we dig in our own archives and looking for simulations of protoplanetary disks that were available that we could use for the game. And yeah, the idea was to use published simulations, so peer-reviewed simulations of actual disks that exist in the universe. So you can tell, okay, now you are exploring DS Tau, for instance, which is that protoplanetary disk, and you can play with it. And we used SPH simulations, smooth particle hydrodynamics simulations, because they have the advantage that they are particle-based. So the disk is modeled by a collection of many particles, 1 million particles, let's say. The advantage of that is that the particles are relatively straightforward to export into a different platform, in this case, the video game. And we used Blender to design a spaceship and Unity to build the game. Maybe you've never heard of Blender and Unity, but they are standard tools of the video game industry. So that really allows us to produce something that looks nice, that looks like an actual video game. Actually, these are not images of our video game. These are images of other games that we used to inspire us. So we didn't copy these designs, not at all, but we were aiming for something like this. So we wanted the video game to look as a video game and not just as an encyclopedic app, right? So here it is, the first snapshot I'm showing you from our game. This is how the cabin looks like. This is when the game starts and you are still at home in the solar system. So you can see Earth from the cabin. This is a little bit a quick view of the ship. I'm going to show you a bit more later, so don't worry. It was probably too fast. And we're already traveling, going faster than light. That's not physically possible, but in games it typically is allowed. So we are going to reach our destinations. Before I show you our destinations, let me just show you one snapshot of showing how we were working. So this was mostly done during the summer with 3 internship students. And here we are we are trying out different illuminations, different textures for the particle data. So you can notice there's 2 colors, for instance, and that's because we have dust particles and gas particles. We treat them differently, so you can take advantage of that distinction in the game. This is another view from the game. This is inside the ship, not in the cabin, but like in the main central area, I would say. And here you can see one of the protoplanetary disks out of the window. And now I want to briefly show you the different systems we included in the game. So I'm going to show you like an actual observation, a snapshot from the simulation, from the hydrodynamical simulation that we used as input, and then I'm going to show you how it looks within the game. The first level, the first system you visit in the game is the STAU. This is a rather simple looking disk, just one noticeable gap. So that can be explained just by one planet. You only put one planet in orbit around the star embedded in the disk, and if the planet is massive enough, then you create this structure. So the gas, as I showed earlier, it tends to remain with a rather uniform distribution, but with a noticeable gap nonetheless, and a bit of a spiral pattern. And the dust shows much sharper features. So a ring in the outside of the planet and a very deep gap at the planet location where the planet orbit is. This is a simulation performed by Veronesi et al. And she kindly, as all other simulations we use, she provided us the simulation snapshot to include in the game. And this is how it looks from the cabin of the ship. And so you can see that there's two colors in the matter distribution. So orange shows the dust. So there's the inner part of the disk and the outer ring, and nothing much either in between or outside the ring, while green shows the gas distribution, which is much smoother. And there's and the spiral is highlighted here. That's why it's hard to see in the green distribution, but it was there. And the way the game works is that you have to approach a feature and then you learn something about the system. In this case, we had just approached the spiral wake created by the planet, and you get an explanation that tells you the gravity of the planet produces this spiral wake, which is especially noticeable on the gas. And this explanation is given to you by this avatar. And something that I think is very nice we did here is that avatar is based on the person who developed the simulation. So in this case is Benedetta Veronesi herself telling us all the features of her disk. The second system is PDS-70. This is rather well known because it's one of the first systems in which we have a pretty solid confirmation of planets forming there. And this is an ALMA image, and here on the right of the star, we see a peak of emission, which is identified as a circumplanetary disk. So that's a disk surrounding the planet that is forming within this gap. And here is the simulation that reproduces that behavior by Tochi et al. And so this is similar to the previous case, but rather than one planet, there are two planets. And given their masses and how long the simulation is active and so on, rather than having a gap here, you have a larger cavity that goes all the way to the star, both in the gas distribution and in the dust distribution, although the dust distribution on the bottom here is much narrower. And this is how this looks in the seen from within the game. Here, the player just discovered the circumplanetary disk, so that's highlighted here. And you can see the gas distribution extending out, the dust distribution being much more confined to this narrow ring. And this is Claudia showing us her simulation. The third system is HR8799. This is a debris disk observed with ALMA. This is the observation by Booth et al. From a few years ago. A debris disk is one in which there's no gas left or very little gas left. So let's say there's no gas left. And this system is well known because inside, in the inner part of the debris disk, there are 4 planets that we can observe directly. And we can actually, we have actually observed them for, well, more than 10 years now, and we can see them orbit around the star, which is a pretty impressive view. For this system, we actually didn't have a simulation we could use, but we wanted to include it in the game, both because it's well known as it has the 4 planets and to have an example of a debris disk. So rather than using a simulation, we use a parametric model of the dust distribution of the matter distribution in the debris disk, developed by Faramas et al. And she actually produced a particle distribution starting from one of these profiles. I think profile model 2 was the best one. So she produced a distribution of particles that we could then input in the game. And here we are inside in the inner part of the disk. As you can see, we are much closer to the star now. So we only see one part of the disk from the cabin. And as you can see, there's only orange. It looks only orange because there's no gas. And also, if I may say so, here you can see how beautiful the stars and the planets look. So we, they are illuminated by the star. So depending where you stand, you will see different phases. And yeah, I think it makes it look much more real that way, rather than having one gray sphere just sitting there. And this is Virginie showing us her particle distribution. Now we go to IRAS, that long number there, which is a binary star, a binary protostar. Here you can see the ALMA observation that clearly show 2 point sources in the center. And around the binary, there's this distribution of matter, which is not symmetric, not at all. It's brighter here on the right. There's more flags coming from the right. This was simulated as a circumbinary disk by Ragusa et al. So here we have his simulation. On the left, there's the gas distribution, where you can see the spiral arms, spiral streams actually going all the way to the binary, feeding the stars material from the disk around it. And the dust distribution shows this vortex-like structure. This is a result of the interaction between dust and gas, and well, with the torque of the binary, you end up having this kind of structure, which would correspond to the overdensity we see here on the right, on the ALMA observed image. Now, if we go to the view of the game, here you can clearly see both stars. Notice these stars are red because they have low masses compared to the previous case in which the stars was bright blue, as it was a high mass star. You can see the gas distribution, the spiral arms going, spiral streams going from the inner edge of the circumbinary disk all the way down to the binary star. You can see some dust accumulation in the small disks, in the circumstellar disk around each star, and the rest of the dust that remains outside. And this is Enrico showing us his simulation. And the final system I'm going to show you this way is HD 14306. In this case, there's a very clear asymmetry observed in the infrared with the VLT. And also we see that there's like different rings. So there's some emission coming from closer to the center and more emission also coming from further out. This can be explained in a configuration in which there's a binary star which is inclined with respect Here you can see on the bottom panels, the edge-on view. You can see more easily how the binary is inclined with respect to the outer disk. And there's an inner disk that aligns with the binary. And that misalignment between the outer disk and the inner disk is the reason for this asymmetry, this observed asymmetry, which is reflection. It's like putting an inclined mirror there, right? So there's the two stars, an inclined mirror, and you see much more brightness coming from the lower part. But to make this work, you need one more ingredient, which is a planet somewhere in between that carves a gap. It cleans up a gap here, and that allows the inner disk to separate. It remains. So it lets you have these two independent disks. So an inner disk that follows the binary, an outer disk that is there probably because just of the initial conditions of the system, and the planet in between that separates both of them. And yeah, there's the tip, as I showed you before, there are these spiral arms or streams that are more easily seen in the gas, not so much in the dust. And this is how it looks in the game. This is one of my favorites because it really lets you see the three-dimensionality of the system. Here the inner disk is highlighted, the inclined disk. You can see the binary inside that disk, and you can also see the planet being half illuminated by the stellar light, and yeah, the spiral wake and so on. And this is Julia Balavio showing us her simulation. Right, so in the next couple minutes, I didn't want to finish my presentation without showing you a short video of how the game looks like. So I'm going to show you the last level of the game. This is Pedro's simulation I showed earlier of this system with a binary and a planet also. And this is how the game looks like when you play it. So you can turn on the dust and the gas separately. That lets you see either structure as you wish. And you can also see the goals, the objectives you have in each level. So you came to the system, you don't know what to do, so you can press ESC and see the list of items of objectives you have to find. The first one in this case is this ring. So the player found the ring, and then Pedro tells you that the disk has this ring of dust, which is rather clumpy. Now we also found that there's a gap and a ring that are most easily seen in the dust distribution. Okay, you found those two objectives, but there's more. For example, there's the planet. That planet was hard to see. It's a bit far from the star, but once you find it, you hear from Pedro that that planet is the responsible for both the gap and the ring. Now we also found this spiral wake, and finally we're going to find the secondary star. And here you can clearly see how the star is behind the plane of the disk. So as I mentioned in the beginning, you really take advantage of the three-dimensionality of the data. As opposed to just showing a picture, here you can go through the disk, look at it from different angles, and realize that the star is behind. Now that we found all the main objectives in this system, we can explore the ship a bit. There are screens with pictures. So here you can see how the system looks from Earth. There's some information if you want to read more about the system. And there's a hologram that's like Star Wars, you know, when they make plans, and you can kind of turn on an immersive mode, and you can have a much better view of the hologram. And in the hologram, you can review all the objectives, all the ingredients you found. So this is the ring and the gap. There's the planet in red. The spiral wake. So you can see again everything you discover from the system in the system. You can see it here. And finally, there's an elevator. You can go down and onto a sort of observation desk. So you are below the floor where you were before, and you have a much cleaner view of the system to contemplate. All right, so that's pretty much it. We want to release this as a beta version among the collaborators, among the MPF community, and so on, very soon. So there's just 1 or 2 bugs that we want to get rid of, and once that is done, we plan to release this pretty much what you saw now. And after that, we want to add a few more things to make it a more professional video game. So have an introduction, a tutorial, have credits, upload it into the Steam store or something like that. So to make it really a video game people can download as any other video game for free, of course. After that, there's several possibilities to continue this project. For example, perhaps the most technical one is, rather than plotting all particles as we are doing now in a brute force kind of way, we could use proper SPH interpolation. So use the smooth particle hydrodynamic technique to make a smoother field, you know, so it looks even nicer, I think. We could add more snapshots, so you see time evolution within the game. You see the disk evolving. That would be nice to have. Obviously, we want to add more systems. And I think in the future, once we publish a paper with simulations, we should at the same time release a new version of the game where you can see the simulation in the game. And finally, we want to go to develop also a virtual reality version. So you can put goggles on and get immersed in the simulation. Thank you very much.